Okay, good. So welcome everybody. This is the session 322 on architecting engineering systems. So I'm Kevin Otto at Aalto University, and I'm looking very forward to this. I'm interested in this topic and all of these papers. I'll let you read the titles and the names, but I do want to say our first speaker is not going to be, our first paper is being represented by Steffen Kunnen on a reverse architecting approach for system architecture. Our second speaker is here, Jarkko Pakkanen on partitioning types. Our third speaker is here, Bertram on engineering to order rationalization and issues there. Our fourth speaker, Julian Rediker, is going to speak on automated part decomposition. And I would like to announce and congratulate Julian and his authors. This paper is a reviewer's favorite. All right. So it's fantastic. It's a great paper.
Thank you.
They're all great papers, but this is a reviewer's favorite. So you will get, you and your co-authors will get a certificate to this effect after the conference. It's one of the top 10% reviewed papers in the entire conference. So congratulations. Fantastic work. Yes. Lastly, Inigo Fernandez will be speaking on technology integration challenges at two global OEMs. So the way this works, of course, is these have been pre-recorded, so we will play through these all together in sequence. And as you have questions, I would ask you to type them into the chat. And then after all of the presentations are done, then I'll go through and ask questions of the authors based on what people typed in the chat, if we can do it that way, because we only have a certain number of slots for people to speak. So that's how we'll do it. So please type your questions into the chat. With that, Robert, do you want to go ahead?
Hello and welcome everyone. My name is Pluhnau and I'm a research associate of the Institute for Product Engineering in Duisburg. For the next few minutes, I would like to present my reverse architecting approach, which can be used to analyze system architectures of existing product families. First of all, I would like to give you a short overview of my presentation. I would like to introduce you into the needs for the development of such an approach, followed by the basics as well as the concept of the approach, and I will conclude my presentation with a short summary and an outlook. So why do we need a reverse architecting approach? Product development just rarely begins on a white sheet of paper. The majority of the activities of development departments is based on adaptation or variant construction. By variation, the design or solution principle, or by extension, the functional scope, new variants and new generations of products are created that fulfill defined customer needs. These generations and variants are characterized by a high level of reusing existing solutions in which new concepted elements have to be integrated. The impact of a variation or extension has to be recognized and considered very early. For an efficient development, an abstraction of the concrete product is necessary in order to recognize the characteristic properties and functions of a variant and to describe them systematically. This abstract description of a reference product can be used for the variation in conceptual as well as the design stage. System architectures offer themselves as a useful reference due to the fact that they represent the functional as well as the physical view on a system. In industrial practice, the architecture description is close to a reverse engineering process, in which products are analyzed for their structure and adapted to changing boundary conditions. Therefore, a reverse architecting approach is presented, which can be used to analyze existing product families in order to describe their architecture. In the following, I would like to describe the fundamentals of system architectures, as well as the concept of the solution approach. So what is the system architecture? As seen in the figure, on the one hand, it describes the functional structure of a product by considering the composition of single auxiliary functions. On the other hand, it describes the composition of their physical components. The functional description is very abstract and solution independent. It represents the customer needs. The physical description reveals the chosen components. These two structures are connected by the logical structure. It describes the used physical effects, solution principles, or technologies that fulfill the required functions and constrain the design. What we got from the introduction is that we want to have a sufficiently abstract description of the product family to use it as a reference for the variation of design, principle, or the integration of new functions. The reverse approach is intended to abstract existing products and families into a functional description and to describe the relation between elements of different abstraction levels within the system's architecture. It is based on the classical stages of the product development, the functional, logical, and physical stage, and it starts by analyzing a reference product structure, which maps different variants in one single structure. Starting from the physical structure, the relationship between function and design is determined by a systematic analysis according to the following model. In the first stage, all existing variants of the product are analyzed with regard to their characteristics. By layering the structures of different variants, standard components, options, or individual solutions can be identified. They are represented in a reference structure, the structure of a theoretical product which contains all possible characteristics using variation points. It is the basis for investigating the cause of different variants on a logical and functional level. In the black box stage, the interaction of the product with its environment is considered. Taking into account the possible operating states, the incoming and outgoing flows of material, energy, and signal are analyzed. Interfaces between the product and its environment are thus revealed. For the analysis of the internal structure, the transformation of the flows crossing the system boundary is analyzed in the use case stage to determine the main functions of the product. Secondary functions required for operations are also analyzed at this point. In the following functional room stage, we analyzed the relationship between the shape and the function of the product in more detail. For this purpose, functional rooms are determined. They describe imaginary design spaces that assume a defined function. A kind of modular functional architecture is formed in which various functions are combined to a functional room. These function spaces are detailed into the concretization stage. Granular function spaces are generated which contain the subfunctions of the superordinate function space. The result is a detailed architecture that describes functions and system flows linked through the interfaces. In the physical to functional stage, the function spaces are linked to the physical structure by analyzing the solution principles. The function-shape relationship is described. So let's summarize the key facts and give an outlook. The presented approach is to be understood as a guideline to analyze the architecture of product variants. It helps to build up a complete system understanding and to find the reason for different variants. A layout supports the activities by visualizing the functions, flows, and interfaces of the system, which are determined in different stages. It is to be used for the computer-aided modeling of architectures. This will ensure information consistency in the development of new variants and generations. The effect of a variation on the different elements of the architecture thus becomes apparent. It supports the integration of new functions or the variation of principle or design. For the application in practice, the approach should be extended for computer-aided modeling. Thank you very much for your attention.
Hi, my name is Jarkko Pakkanen, and the title of our paper is Partitioning Types in Product Modularization. The overall aim of our research is to support finding beneficial model structures in different industrial modularization projects. Objective of this paper is to present alternative partitioning types to support dividing a product into modules. We have two research questions. The first one is what other alternative partitioning types than functional partitioning can be identified, and second, how the descriptions of identified partitioning types as a design guideline affect the quality of the result in modularization projects. So we answer these research questions by this modularization challenge. In this challenge, teachers act as a market and customer view, whereas master level student groups act as a wheel order suppliers. Each student group can select from a list of variation needs which variation they are going to pursue into modularization. And some variation is more challenging to implement than other, but if the student group tries to implement this challenging variation, they enable also better grades. And these variety requests relate to boom and bucket solutions, front carriage and rear carriage structures, and also to power line and steering systems. The wheel loader has to be configurable based on the predefined and documented module system without the need to rebuild the entire product when a customer orders a particular variant in the sales event in the end of the course. And then there is also this 5-minute assembly time limit to motivate the students to design a modular, predefined and documented structure. Students have designed different modular wheel loaders during the years. Some examples from the 2019 course are presented in this slide. As you can see, many of the wheel loaders have some kind of large element to which the module variants are attached to. Based on 2017 and 18 courses, we described what are the main partitioning types the students have and could have used in the modularization work. The key partitioning types to use in module partitioning are big and small building blocks, big common element, multifunctional core element, frame-like base element, or function-based elements. Next, we discuss what kind of properties these different types have based on the modularization challenge. Two groups selected big building blocks partitioning type, but both groups found it too demanding. In 2019, none of the groups used small building blocks partitioning type. 1 week and 2 good wheel loaders were built according to big common element partitioning type. 5 groups used multifunctional core element partitioning type, and none of the machines were weak. 1 group designed the wheel loader according to frame-like base element, and it was good. None of the groups used function-based elements. So here are the conclusions. The key aim is to develop design support for finding the most suitable partitioning type in each modularization case. We presented alternative ways to partition the product into modules, and in 2019 modularization course, 10 groups that participated got to choose the partitioning type they would follow in this Lego exercise. Some repeating patterns were seen, but we have to remember that the sample size was quite small, and this has to be taken into account when analyzing the results. More analysis of previous course implementation is required to draw more detailed conclusions about the benefits and challenges of each partitioning type. And also we have to remember that in industrial reality, different sections of complex modular products may be based on different partitioning types, not only one. This was realized also by our students in the latest 2020 course. Thank you.
Welcome to this Design 2020 conference presentation titled Why Engineers Order Portfolio Rationalization Stall, Challenges in Standardization, Modularization, Platform Design, and Mass Customization. My name is Christian, and I'm doing a PhD project at the Technical University of Denmark titled Data-Driven Portfolio Decisions for ETO Profitability. So, comparing ETO businesses to other types of businesses, we can do that on customer order decoupling point, so the point to where we can push our own customer solutions and where we rely on the customer requesting a certain solutions. Comparing to select variant, assemble to order, configure to order, modify to order, and then lastly engineer to order. And this is where we engineer the entire solution to a specific customer request, working with defined norm, standard concepts, or even systems and system definitions and system structures. The ETO way of working is that the customer requests the product, we rely on them to request something, or we offer an abundance of variants which they can choose from. Then we engage in sales negotiations, design, engineering, manufacturing activities, and then finally qualifying it for delivery, and finally delivering or handing over the final product, being that a plant, a bridge, a ship, whatever, to the final customer. So this initial variance is slowly degraded or focused through our decisions into the final product that we're delivering. Looking at it another way, we say that our initial decisions have a very high impact on the product. So we can decide on cost allocation, the system structure, system names, performance strategies, and so on, while not knowing exactly what we're going to deliver until the end. So at the end of the process, at the end of the project, we know exactly what we have delivered. We have a high knowledge of our solution. So as you can see, in the beginning, where we have to take the really big, important decisions, we don't know what we are exactly delivering. This brings about a little complex or a little paradox that we want to solve. Can we limit this internal variance, so this internal way of working where we rely on everything being different, while still maintaining the external variety, so the market attractiveness of us being able to deliver or offer everything the customer needs, as we are an engineer-to-order company. There are different rationalization tools to do this: the standardization, working with a fixed solution space, modularization with fixed modules or fixed interfaces, platform design being a combination of generational design and modularization, and then, of course, mass customization and configuration, working with very late customization of products. Using some of these tools, of course, brings about different challenges. So if we're instance using modularization, we need to know exactly how to develop modularized products, and we know exactly what modules we should deliver, what the market needs, how do we actually optimize our way of working and still maintain the offerings that the customer needs. We can aggregate these challenges, so looking across the different tools and all the different places where it's been used, and then combine that to one big list of challenges and roadblocks. That's what we did in this contribution, where we looked into literature, trying to extract the different roadblocks and challenges that they have seen and experienced and described when using these tools, and then comparing that to a few different case studies and industrial case studies, extracting the problems, challenges, and roadblocks that they have using these tools. That turned into one big aggregated list of challenges, and that's the contribution of this article. So a few examples of that. Three of the case studies and in literature, they agree that the disbelief in defined solution spaces is a big challenge, so that, for instance, the organization is not keen on defining too strict limits of what we can do. We might have a sheer resistance to actually changing status quo of development. We might have a difficulty in obtaining the information that we need about our past sales to actually figure out what we should standardize. We might not have a process that's suitable for this kind of tool, so it might be too knowledge-driven and not really codifiable. We might have that rationalization won't have any effect because we simply customize too much, or we will have nowhere to actually put the final results. That's the two main themes that we found. One, we can't find the information we need, and two, that we lack a place to actually put our results, a place where this could actually live. That was it for me. Thank you very much. We invite any questions afterwards, and enjoy the rest of the content.
Good afternoon, ladies and gentlemen. My name is Julian Redeker, and I'm a research assistant at the Institute for Engineering Design at the Technische Universität Braunschweig in Germany. And today it is my pleasure to present you our paper, Automated Part Decomposition for Product Architecture Modeling, in the context of the novel manufacturing approach called incremental manufacturing. The global customer spectrum, global competitors, and the growing demand for individualizable products are increasingly challenging the industry. So besides the rising complexity in product development, conventional manufacturing processes such as injection molding are reaching the limits of economic efficiency. And one novel approach that promises a cost-efficient and scalable production of customized multi-material parts is incremental manufacturing. IM is a robot-based manufacturing strategy in which products are assembled from pre-produced parts first and then finalized by additive and subtractive manufacturing steps in a single working cell. But besides the potentials, the approach also raises new challenges in product design and production planning. So one contribution to handle the resulting complexity in redesigning parts for IM is the procedure model for integrated part design and process planning. Basically, this model can be divided into the two core modules, combinatorial generation of part topology and combinatorial generation of production sequence and evaluation. And the focus of this presentation is on the first module, where part concepts for IM are automatically generated on the basis of a predecessor part. And hereby the reference part is decomposed into monolithically manufacturable segments, which are then assigned with suitable materials and manufacturing processes based on previously derived heuristics. And in order to achieve a high degree of automation for the entire procedure, and to get the possibility to analyze even vast solution spaces, it is necessary to automate the part decomposition procedure. And this is the scope of this contribution. Well, all further steps of the redesign are based on the successful decomposition into segments that can be manufactured monolithically, and which is initially strongly driven by the geometric attributes of the part. And furthermore, the approach should provide an extendable basis for subsequent analysis and design tasks, like a platform candidate detection or part consolidation strategies. So humans are easily capable to abstract the shape of an object, to decompose it based on geometric properties, or to group multiple objects based on shape similarities. And the research field of 3D shape analysis is dedicated to these mentioned tasks, which is still challenging to computers. And to overcome the issue that only a few state-of-the-art algorithms seem to be capable of a fully automated segmentation of mechanical parts, we present a novel approach that could contribute to a high degree of automation in 3D shape segmentation. And so the main procedure of the mesh segmentation algorithm is shown in the figure on the right. And here the input boundary mesh, for example, an STL file, is treated like an undirected graph. And the edges connecting the nodes are weighted based on geometrical attributes. And on this basis, the distance matrix, which characterizes the geometrical distance between each element of the boundary mesh, is assembled. And by the application of a density-based clustering approach, groups of elements with similar geometrical connections are detected. And in the last step, following the minimal rule, these match patches are then merged if they share a boundary characterized by a concave angle. And this leads to the final part segmentation. And when applying the algorithm to models from the ABC dataset for geometric deep learning, reliable results were obtained in most cases, and which indicates good segmentation results for further similar shapes. So, due to the multi-stage procedure and the graph-based approach, a simple extendability of the method is given. For example, the results from FE analysis can be mapped on the graphs in the post-processing stage, for example, to avoid segment boundaries in areas with a high stress concentration. And further, the potential for the subsequent redesign steps exists, for example, in the implementation of design feature detection based on the segment geometries and the topology of the patch graph. In addition, the segment graph can serve as a basis for the automated assignment of suitable pre-produced parts and manufacturing technologies by using methods from the field of 3D shape matching. And finally, by comparing multiple product graphs using graph matching approaches, for example, standardization potential within a product family can be identified. In summary, a high degree of automation in the segmentation of mechanical parts with as few input parameters as possible is achieved. Furthermore, it enables a fast analysis and optimization of product families based on the concept of product architecture. Finally, it provides the foundation for an integrated redesign and process planning for incremental manufacturing, and thus a cost-efficient and scalable production of customizable multi-material parts. In the future, further heuristics from the area of platform candidate detection and part consolidation will be implemented in the algorithm and applied to further parts and part families. And on this basis, functions for the automated allocation of pre-produced parts and manufacturing technologies are integrated. Thank you very much for your attention.
Hello, my name is Íñigo Alonso Fernandez, and I will be presenting the paper with the title Identification of Technology Integration Challenges at Two Global Automotive OEMs. This paper was co-written by Massimo Panarotto and Ulla Isaksson at the Chalmers University of Technology, and with the collaboration of Volvo Cars and Volvo Group Trucks Technology. I will first introduce the topic of the study, then describe the methods we used to conduct it. Then I will describe the results we got and follow up with a discussion of what we learned from those results. And finally, I will draw up some conclusions and pointers for future work. The study revolved around the overlap of four main topics: product platforms, the automotive sector, new technologies, and the design process. We will argue that a model-based approach might help in making better decisions about the trade-offs that the identified challenges present. To support this, we conducted a review of the literature focusing on the overlaps of the different topics mentioned earlier, keeping the design process as a constant in all the searches. We collected issues and challenges reported in the literature as encountered when integrating new technologies in existing automotive platforms. Additionally, with the collaboration of the two OEMs from the title, we carried out workshops with the participation of the roles listed in this table. They were experienced experts in their domains, currently collaborating with each of the companies on new systems integration. We also had some additional interviews to complement the selection of participants that could attend the workshops. During both the workshops and interviews, a questionnaire was used as a guide and as a way of collecting responses, but discussion was encouraged in a semi-structured manner. From the data collected at the workshops and interviews, we produced this table of change drivers and constraints. The change drivers were categorized as external, internal, or driven by technology push. The constraints were divided into time, cost, regulation, and organization constraints. We also collected data on the challenges in the introduction of new technologies from both the workshops and interviews and the literature. Some of the challenges described by the participants are not recorded in the literature with the specificity of being present when integrating new technologies in existing automotive platforms that have been described in other contexts. The challenges related to product platforms were mainly concerning interface management and emergent characteristics like the different entities. The more automotive sector-specific challenges were related to the after-sales service and brand management. The new technologies impacting the most in these sectors were identified as the electrification of the powertrain and the digitalization of the user experience. The design process challenges were mostly around the length of the development lead time and various organizational issues. Common to the challenges identified is that they present themselves when trying to balance several parameters or decisions. A model-based approach might help making better decisions about the trade-offs that the identified challenges present. To conclude, we investigated the challenges found in the integration of new technologies into automotive product platforms. There is little report in the literature on the assessment of trade-offs between the compliance to existing product and process platforms and the user utility or value offered by introducing new technologies. Moreover, the methods available in the literature are not well known in industry, and our findings highlight a normative gap in the current automotive literature on how to approach this process and overcome some of the current challenges, such as the early availability of value models to assess, for example, the impact of flexibility and other entities in the lifecycle value of product platforms. Providing the development teams model-based tools and methods can support the decision regarding trade-offs between platform changes and platform flexibility. The identified industrial challenges require multiple factors to be traced simultaneously. There is latent potential for a model-based approach to make value-informed architectural design decisions about the integration of new technologies.
Okay. Thank you all. So if you have questions to the authors, could you please type them in as we go here, and we'll allow the authors, speakers to address them. So one of the first questions that came up was from Christian on to the reverse engineering first paper.
Yes.
Yeah, so it was asking about you know, how does reverse architecting differ from reverse engineering because it perhaps appears that you're dealing with a single product. So what's the, and also a parallel question is what's the scope of the product family you're looking at?
All right, since I'm a substitute, I try to give my best to answer all the questions, but if it's not enough detail for you, please ask Mr. Pluhnau directly. But first of all, our main goal is the efficient development process, and we want to set a standard for future constructions. So all the products currently under development are not built under these standards. So, for example, what happens when we want to develop a new product or an adaptation of a product family or a new variant? Usually you just have a physical part and you just add it to your current product, or you substitute anything. So you're pretty much limited to a solution space. You just know what you want to do. You don't look on the left or on the right. You're pretty much limited. So our approach aims to add a function and not a physical part. But therefore, we need the system architecture which connects physical to logical to functional space. Maybe it gets a bit clearer if I just give an example. Nearly everyone knows what an e-scooter is. They are pretty much all around right now, but some of them don't have a lighting system. So we have the problem that it's too dark outside, we can't see anything. If you want just to add a lighting system, you don't know which functionalities are affected. So, for example, it would be very much easier for us if you know which functional module will be affected. For example, the providing energy. So you know if you want to add a light system, you just don't add the physical part. You have the affection of different other functions which are connected to this problem. So it would be easier if you just add the function and then go on to develop your solution, instead of just adding the physical part and go back to your functional level. So for your future, for our future test, we have done it on an e-scooter right now. It worked perfectly, but I think as Christian said, it's pretty much very much different for single object or for different modularized objects. Future activities aim towards looking at different types of product and how the structures are affected by this approach we have. I hope that gives you like a small impression of our main goal, and if this answers your question. But most important, our standard or our approach aims at generating these structures for products which don't have these, and set a standard for future developments.
Okay, thank you. Another second question was to Jarkko. Are there examples from industrial products that use any of these partitioning schemes that you showed, or do you think there's usually some sort of combination of these used?
The products that I have seen in manufacturing industry, they are typically very complex products and consist of different design areas, and so I think that the latter answer is correct, that they are typically some kind of combination of different partitioning types, and the key thing is to recognize what kind of partitioning type would be beneficial in each design area of the product, and that is one major challenge in modularization.
I have a question for you as well, which is, as you presented some of those alternatives, you said, two groups use this and the results were no good, or three groups use this and the results were good. I'm wondering, what does good mean? How did you assess that?
Well, basically, we had like this kind of variation requests. And also the students had to, we had a test drive in a track where they need to do things with the wheel loader, and according to that, it was really much simplified, this answer to that. Yeah.
Curious.
So the students selected in the beginning of the course that what kind of variation they would pursue, and then we analyzed in the end of the course that how well they managed to implement those module variants in their wheel loader, and how well they managed to manage with their wheel loader in the modularization day where they had to drive.
I see.
The wheel
It
loader.
looks like a great course. I want to find more out. Maybe
Students
I'll
have
do
liked
something.
it very well. Yeah. And if anyone else is interested about more details of this course, we are, of course.
Good.
Then I suggest you do it remote.
Yeah. Okay. Moving on, and if you want to say more, please do. There's another question to Julian on the fourth paper on automated decomposition. Yeah, is it possible to let the algorithm assess if the decomposed parts are sort of identical, and to get at the degree of variety of parts or commonality?
Yes, well, at the stage of when we wrote this paper, it wasn't implemented, but now we use techniques of shape matching in the field of 3D shape analysis. So therefore, we are able to detect similar shapes, and by using this abstract graph representation, we are also able to detect patterns within the product architecture. But at present, I think we were only focusing on the physical structure, but we are also working on how to enrich our analysis model with strategies of machine learning, with or how to label them with functional aspects, like, for example, how to detect design features like ribs or holes, or if we apply these shape similarities, if we already got a labeled database, for example, where already some functions are integrated, so we are able to map this on our analysis graphs and to process it into the overall product family, and therefore to detect high potential areas or subparts for standardization, or what are variant features, and applied to our manufacturing approach. We are trying to achieve these standard structures should be manufactured in mass production, and then we only add the variant features with our additive manufacturing strategies. So this is the basic motivation right now. I hope this answers your question. Okay.
I have a follow-on to that, which is I was curious how the assembled features that you identified, basic, shape, how did they compare with, when you do feature-based design in CAD, you select fillets, did you reconstruct those, or are they completely different? Are they analogous? Are they, how did they compare?
I'm not sure if I understand your question right. So you mean how to detect these features within our product representation, or?
Well, you detected some features.
Right. Yeah.
You said, hey, here's the cylinder in this thing. Here's the disc that went around it, right? And these are holes. Okay, so if I were to design that part in CAD, I would start and I'd make a cylinder, right? I mean, that's a cylinder feature that you start with. I would add, a hole is a feature, that are just selectable in the CAD software, So did the features you identified out from the CAD using your AI, how do they compare with if I were just sit down and create it from scratch? Do I get the same features?
Yes, well, right now this is basically at this stage the analysis tasks. So we're able to detect these features in previous designs or in existing designs, and then the next stage will be after this identification of standardization parts. We will map these previous parts on it, and then we will perform topology optimization to get our new design proposals or our shared design proposals. So this is at this stage more or less not included to add new design features, but with this analyzing strategy, we hope that we also be able to detect, okay, so if we move this design features to this subpart or within our product representation, so if we move these design features, we are able to achieve a more or a higher degree of standardization.
Okay. More questions, people? To Inigo, I have a question. So there, you showed the challenges of introducing new technology that happened at these companies. So this is very cool, very interesting. Was the problem that these companies have, is it that there's no tools to be able to do this, or that the people in the company are unaware of, you know, methods in the research that they could be using? You know, where do you see that?
I think it's both. It's definitely there are methods out there. There is sometimes overabundance of methods, and one of the main problems is that they are difficult to implement when they are presented as a whole. You know, change your whole way of working, and you know, the promises things will be better for these use cases. So one of the problems is that the methods that exist are not being implemented, or for whatever reason, not known or difficult or whatever. And the other part is that some things are not really present as a specific enough solution. You see maybe some frameworks and very vague solutions out there, but where you actually need to implement it, it needs to be so customized that it seems like an effort that companies are not willing to make for a small quotes problem that they don't encounter maybe that often. But the issue with that is that when they do encounter it, it might set them back a lot when a new breakthrough comes out from technology push, or a new fashion thing comes from the market pool. They might not have the agility to actually use the platforms that they are currently working with to implement the changes needed to integrate these new technologies or new ideas. So yeah, it's a problem, but sometimes it's not such a big problem, so it gets ignored, and the tools are not there in maybe usability or practicality. So it's a bit of everything that gets together and gets them in a situation that is not optimal.
Interesting. So I guess when I was reading this about introducing technology, new things into the platform, I was thinking about change propagation works, and you know how much is this new technology going to change everything or not? You know, and so I was wondering if any of that would be useful to the problems you encountered.
Yes, definitely. I think there was a reference to some of the Claudia's work. I think she's also in the audience. And definitely, but one of the things that is needed for that is in early phases to have kind of, as we said on the presentation, a model of what you're trying to achieve, so you can run these methods against something. When you're trying to make decisions very early on, it's difficult to keep the thread of what are you actually changing or not, and what changes might happen in the future, unless you represent this in a more tangible way than just a description in a Word document or something like that. So that's where we see one of the gaps. So try to encourage companies to start modeling these things early on, so they can apply these existing methods to track these things.
I see. Interesting. Okay, so keep typing in questions, please. Julian, there was a question here on what was your correct detection rate? How many of the detected parts were actually separate parts and not just shape features?
Well, I'm not sure if I understand the question in detail. So maybe you can specify it a little bit more. So because, well, if you mean the detection rate in constant, so we applied our segmentation algorithm to a database or a benchmark data set of about, and there we selected about 100 parts. And for these 100 parts, I think we achieved for about 95 parts reliable or good results in segmentation, so that we say, okay, this is a plausible segmentation result. So we have these subparts which can be manufactured monolithically by one of these implemented manufacturing strategies in this incremental manufacturing lab, and that was really good. But yeah, sure, when applying it on really complex structures or really large assemblies, it's pretty hard. Also the computational performance, so we have to work on it.
I see. For the automatic detection part again, what do you, wait, is that right? AD. What do you mean by reference is a question. Actually, that's for the first talk. So that goes to Stefan.
Can you repeat? Because I was kind of focused on the chat right now.
Oh, sorry. So there was a question on that you had a reference architecture as part of your approach. So what do you mean by reference?
Um,
Do you think that introduces bias into the results?
Just give me 1 second. You'll think about it. Is it regarding the discussion we have with the product family or the, what is it called? Give me a second. Sorry, I didn't get the question right, I think.
All right, well, we can answer it later too, some other point, but you know, there was a reference architecture that you came up with as part of this, and then against that, you would introduce variety on aspects of it to construct a family, as I understood it. So that seems sort of important and might be an opportunity to restrict or bias what you mentioned the result of it.
I think it's a question regarding our discussion. It was the question if you can adapt our approach on just a product family or single products, and I tried to answer in the question in the chat right now. What we are currently researching is exactly that question. How does it affect different types of products? For example, these product families. And for product families, we came to the conclusion in our research that all of these are based on one reference architecture. So, this architecture is usually on the functional level. So we don't look at the physical side of these products. For example, if it's all done by one solution, for example, lighting or the wheels, for example, we just watch which types of products share the same functional pool. And this way, we want to develop the functional reference or the reference architecture for a whole product family. So it's more like looking at the product on a functional level, not on a physical level. I think it's kind of that regarding the question from Christian. I see you shaking your head. Did you get it? What we mean right now? Because I'm not like the main author. To say it again. But our main approach is the reference architecture on a functional level for future development processes. So if you want to add a new component or a new functionality, it's easier to adapt it maybe for a whole product family, not just for one product.
Okay. Actually, I have a question for Christian on the third paper on why engineering to order rationalization stalls. So, if I understood correct, what you observed and concluded was there's sort of a lack of data that's necessary, information you need to be able to rationalize, and you know, perhaps a inadequate portfolio management, being able to do it. I'm curious though, isn't it hard for companies to, if they're going to rationalize? To me, that means, you know, sort of reduce and make it less engineering and more standard, so it's faster and easier in that sense. But you're kind of reducing or dropping offers that you might make, and so maybe you're worried about reducing the ability to make a sale in the future. So, I mean, is that part of what's going on?
You can say one strategy for rationalization, that would be standardization. So limit your solution space. But what we want to do with especially modularization and platform strategies, that is to keep the market variance, so the offers to the customer, but limiting in how many ways we're working on the inside of the company. So limit the amount of architectures we're working with, limit the amount of solution spaces we're working with, and you can say sort of streamline the architecture of our processes and our products, so we can reuse, we can have common interfaces, we can share, you can say, resources between departments. So especially with engineer-to-order companies, it's really, really difficult because they are thriving on variance to the customer. That's their business plan. That is, we can build whatever you want. Come along, require something, we'll build it for you, right?
Right.
That's their business model. But still, if you are in a business context or in a special business sector, let's say you're building power plants, well, there are some of the things in the power plants that will be somewhat the same between each solution. And if you focus on it, you can reuse these, and you can especially reuse the way you design all of these common parts and common subsectors, right? And that's the whole, you can say, that's the whole goal of ETO rationalization. That is to streamline how we reuse and not necessarily cut down on the solution space. Did that make sense?
I see. Yeah, it sounded almost like the process is the platform.
You can say that. You can say that, absolutely. I think product platforms or product architectures and then process platforms and process architectures, they go hand in hand, absolutely.
Okay, I'm probably getting behind on where we are on questions. Julian, there's a question on how good of a CAD model you need to have for this process.
Okay, so basically the framework works on triangulated geometry representation, so boundary mesh, STL files. So I think there are algorithms to process these point clouds from the scan to this boundary surface representation. But at present, or to be honest, I'm not sure how the algorithm will handle this noise, because if we use a clear defined CAD model and abstract it with these boundary mesh, so there we have clear shapes. I'm not sure if we have, for example, noise in these point representations, so in the heights of the points, how the algorithm will handle it. But it could be interesting to have a look on it in the future.
Okay, good. There's a question for you, Inigo, on how does have you looked into the organizational structure challenges? How much was that with respect to technology integration?
I made a comment on the right now, but to summarize, the main organizational problems that were presented to related to the decentralization of teams and having to work among different continents and the problems with that. And on the other hand, that multidisciplinary efforts are still difficult, despite the efforts by companies to create these kind of cross-functional working groups and matrix organizations and so on. That's where most of the issues that were mentioned came from.
It wasn't then new supplier issues or anything like that, the new group of engineers from a different company that are supplying this new technology?
Not that we saw, and I think this is the case because we were dealing with the OEMs, and in the automotive world, they carry a lot of power and weight. So I'm sure the case is different if you go down the tire list of supplier. But that was the problem.
Okay. Okay. And to Stefan, did you answer this question from Tero on different price points and customer segments? And
yeah, it's kind of a tough question because I'm not quite sure how Mr. Pluhnau or Rowan Pluhnau wants to deal with these questions. Our main goal was the reverse approach. So we are currently trying to figure out if there is a possibility to create these architectures. The next step, if we have the possibility to create these architectures for nearly every product, we would like to implement it in the development approach. And then we have the question, which different price points, customer segments. We haven't decided yet how we want to like approach this problem. That's why I can't give like 100% or exact answer to it. But it's a good question. I will give it to Mr. Pluhnau for future discussions. And yeah, don't let me say anything wrong.
So I thought this session went till, yeah, it does, till 1/4 after. But at the same time, the social gathering is starting. So more questions that people may have, feel free to go ahead and ask if you like. I think we went down our chat list. Well, I really enjoyed the papers. I really enjoyed the discussion that everyone's having here too, and the capture in the chat. So it's really good. This is a fabulous area that I am interested in. So I want to thank you all for attending. I want to thank all the speakers. It's wonderful. So please join the social space. There's a link in the chat, and thanks for all the presentations. Thanks for all the discussion. And with that, I think we're good. Thank you.
Thank you. Bye.
Bye.